Hello, hello. Hey, hello, hello. Let us test. We are joining to the or meeting or event. Hello, hello, hello. It's gonna take a little bit time. I need to check. Hello, 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 hello. Hello, 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 hello. Hello, hello. Welcome, welcome back. Welcome back. Welcome back. Hello, Gabriel. Hello,
Hey Javier,
Julio. How are you guys?
doing all right? How are you doing?
I'm doing well,
Hello,
thank you.
Gabriel.
just a little bit busy because the streaming on YouTube is not working. I'm really sorry about this and try to solve right now. I don't know why. Maybe my internet is not very good. So I'm gonna just turn off the my audio for a while, and then I will be here for in 4 minutes. Sounds good? So
Okay.
Julio, this is Gabriel, professor at Alberta
Hello,
University.
Julio. Nice to meet you.
Nice to meet you, Gabriel. Can you hear me, Gabriel? Is this
I hear you.
I'm
Yeah, I hear you
very,
well.
very
Yeah.
good.
Can you hear
Very
me?
good. You perfectly.
Yeah. Okay, great.
Good. Yeah, nice to meet you, Javier. I think I can hear you very well. Is any issue with your audio?
No, it's with the YouTube channel.
Okay,
Sorry. Yeah.
okay. Oh, nice to meet you, Gabriel.
Where
Your
are you
name
from,
is a
Julio?
Spanish name. Is this speak Spanish?
I don't speak Spanish, unfortunately. I wish I could speak Spanish. Yeah.
Where are you professor from?
I'm in Alberta, Canada,
Okay,
University
good.
of Alberta.
Okay, I'm in Vodafone in the UK.
Uh-huh.
It's very, very nice. Alberta is on the
The
west
west
coast.
side. Yes.
Yeah, that
It's
means
not,
English.
yeah, it's English speaking, yeah, primarily.
Good.
Yeah.
Okay,
It's
good.
so on the west coast we have British Columbia, and then we're the
Mhm.
next province in from there.
Okay,
Yeah.
good.
So
Oh, very nice area.
we have plains and mountains.
Yes, it's beautiful. I don't know
It's
over there, but
yeah, it's
I have a friend and she moved long time ago to Manitoba.
oh yeah, that's
It's in the middle
not
of
in the middle of
Canada.
the country,
It
yes.
was, I mean, she left Guatemala. And I come from Guatemala.
Uh-huh. Uh-huh.
And she left probably Guatemala 30, 40 years ago.
Oh wow. Yeah.
And since she left, she doesn't she doesn't want to come back. She's
Oh
so
really?
beautiful. A lot of problems because the initially the language, because on the west side it's not a problem because it's English,
Yes,
but on the
yes,
French side is both.
yes, yes.
And
Yeah.
then he had to speak Spanish with daughters and son and husband,
Uh-huh.
and have to learn French and English.
Yeah, it's that's part
Okay.
of the integration experience. Yeah.
Yes, of course, of course.
Yeah, yeah.
Okay. And what is your major, Gabriel?
I'm a theoretical computational chemist.
Okay. Oh, chemistry.
Yeah,
Okay.
yeah, my
Because
background is in
well, I did my
chemistry. Yeah.
PhD in computational math and
Yeah.
optimization of energy.
Oh,
That
okay.
means not chemistry, but I did a lot of lithium batteries,
Yeah,
and then I have to learn how the lithium
some
batteries
chemistry.
works, and
Yeah.
yeah, a little bit of chemistry.
Yeah, yeah, yeah.
But it's
Yeah,
very
nice.
nice. Chemistry is good.
So yeah, where did you study?
I did my PhD in Portsmouth University in the
Yeah.
south of England,
Uh-huh. Yeah.
and
And where are you currently exactly?
in London, close to
In
London.
close to London. Okay.
We're in Reading. Reading is 30
Reading. Okay.
miles west.
Okay.
Yes,
Okay.
west.
Yeah.
London, we are 20 minutes with the train. We are in London. Reading
Okay.
is the first big town close to London. There's a lot of towns around
Yeah.
London,
Yeah.
but Reading is big. That means a lot of people live here or
Yeah.
sleep here,
Yeah.
and then
Yeah.
commute every day to
It's
London.
kind of like a suburb of London.
Yes, exactly. And big town, because there is a relative lot of small cities around London.
Yeah.
But Reading is the first really big
Big one. Yeah.
town. Yes.
Yeah.
Yeah,
Nice.
it's and I work in Newbury. Newbury is 30 minutes from here, from
Yeah.
Reading north, in the west,
Okay.
northwest. And
Are you
it's
at a university there?
no, it's Reading. No, it's in Newbury. I work in Vodafone. Vodafone is the telecom company.
Oh yeah, the telecom. Yeah. Yeah.
Yes,
Vodafone.
in the
Yeah. Yeah. Yeah.
UK.
Yeah.
Yes, and it has
Okay.
many countries.
Yeah. Yeah.
And I work for the group, which is the Vodafone has like 20 different companies, and then Vodafone Group manage these 20 companies.
Okay.
And I work for the group. And I mean, it's
Wow.
just not directly from a particular market, because we decide,
Okay.
but not I know, we do all the work.
Okay,
Yeah.
Gabriel
Good.
and Julio, thank you. I'm sorry for
Good.
the for the
Did you
one
figure
minute
things out,
late.
Javier?
I'm sorry.
Did you figure out the YouTube issue?
Yeah, I think YouTube is now working. I have the link. It's this one. I'm gonna
So
share. I'm
after
gonna post
after we
over here.
speak, should we be watching the talks on YouTube, or can we watch them from here?
Yeah, you can. Yes. I mean, you can stay here. I
Okay, I'll
mean,
probably stay here. Yeah.
yeah, you can stay here. And actually, I'm going to start right now. I'm gonna just share my slides. I can see on YouTube right now, actually, and but this is the link. I posted the link. If you want to share people with somebody else, please do it. I see here
Okay.
some people. Please share with your network. This is the link. It's over here. It's on the chat box. Please copy and paste and share with more people. So, well, anyway, so I'm gonna share my screen just to start because Dr. Gabriel Hanna is gonna be here for 15 minutes after 2:10. So just let me start because let me see. Yeah, you can share your slides actually, Professor Hannah. Okay, but just let me start. I'm gonna just take 7 minutes to share with people about this initiative, which is about the International Quantum Discovery Day. So, welcome to everybody. So, this is our first event about the Quantum Day at National Autonomous University of Mexico. This is in Facultad de Estudios Superiores in Acatlán. This is faculty close border to the Mexico City. Actually, we are about 50 minutes from the Mexico City campus, the main campus. So today we have Professor Gabriel Hanna. We also have Powell Gora, which is going to join us in probably a couple of minutes. And also Professor Julio Gonzalez, Science. And this is Javier Ordu. So I'm going to be your co-host. I'm gonna check the YouTube questions. I'm gonna check and I'm gonna pick up your comments from YouTube and also here on Zoom. So please feel free to ask over here, pose your questions, and just I'm gonna try to get all the different comments that you have. Okay, so sorry, what is my slides out? Yeah, over here. So this is the International Quantum Discovery Day event, and this is part of the International Quantum Youth Initiative. This is an initiative that we called us, and QMexico does too, initiatives. Actually, Caldas is a company, quantum company in Latin America. And on the other side, we have QMexico, which is an initiative that I am also the honor to be the founder of those two initiatives in Latin America. So those two have a different profile. The first one, Caldas, is more about companies. We want to develop some software, hardware, and in the future we are going to have more different projects. And on the other hand, QMexico is more about nonprofit initiative. Here we have different events. We also try to promote quantum computing technologies in Latin America. So this is why we are doing this kind of thing. This is actually the last year, 2025, we celebrate the International Year of Quantum in Science and Technologies. This is because we are celebrating about 100 years of quantum computing. Okay, so the last year we celebrate 100 years, and this is because one of the most important work which were created by um, Heisenberg, which is here on this picture on your left-hand side. So you see here that there are different people also contributed to this quantum, not only technologies, actually quantum concept is coming from physics, right? So we have physicists which contributed to all these different topics. For example, Feynman, Planck, Einstein, Bohr, Schrödinger, Dirac, de Broglie, and other people which were pioneers in this area. But on the other side, we also have quantum information and computing, where we have people. This is more a recent topic, actually, and there are more people contributing to this area, such as again Feynman, Deutsch, Shore, Grover, Preskill, Bennett, Brassard, and actually currently there are different people contributed to this area. So, but why we are also celebrating today the World Quantum Day? This is actually because Planck, which was one guy, one scientist who contributed a lot to the foundation on this area, quantum computing, quantum physics, actually. He proposed one important constant, which is called Planck constant, which is over here. It is about 4.14 times 10 to the minus 15 electron volt seconds. So, let me just check something. I'm going, okay, yeah. Okay, so that's the point with this. We are using the first digits associated to this constant, and then we are going to just take and associate one day to this day, which should to this date, which is 4/14. Today is April 14th. So that's why we are celebrating World Quantum Day. Okay, so there are different areas associated to quantum computing, and actually we have quantum computing, quantum communication, quantum sensing, quantum energy, and other areas, which is important because our future, which is current, those different technologies are invading, are in our society. So actually there are different companies such as IBM, such as Google, D-Wave, and other different companies that we are going to talk today in these sessions. So I'm just showing these different slides faster because we are going to talk about all of this, but we are going to focus this in maybe the third session, the third talk, where we are going to discuss more about this kind of things. Okay, so so I mentioned IBM, I mentioned also Google. There are different other companies such as D-Wave. In Canada, there are different companies in USA as well. Europe also have different companies in France, Germany, which are just pushing all these different topics in our current society. So we are going to start with Dr. Gabriel Hanna, which is who is going to talk about an interesting topic, which is quantum batteries. This is a really interesting concept, and he's one specialist in this area, actually. Professor Hanna, I have the honor to meet Professor Hanna. We met in Italy, actually. We were talking about different topics in quantum computing. I know Professor Hanna is working at University of Alberta. This is in Canada, and I know he's a very he has really a lot of experience in this area. So Dr. Gabriel Hanna, welcome to these sessions. Thank you for joining us. We really appreciate that you have time and just you prepared this talk to all of us. Thank you so much. Just for our audience, please share the YouTube link, which is in the box, and also remember you can ask in Spanish. You can put your question in Spanish and also in English, and we are going to just bring those all of these questions to Dr. Gabriel Hanna. So thank you, Dr. Hanna.
Thank you, Javier, and thank you for organizing this International Quantum Discovery Day. I'm going to start by sharing my screen. And to share. Can everybody see that? Yeah? Okay, great. So today I'm going to be telling you about one area of my research dealing with quantum batteries. So we started this research about 7 years ago now, and the title of my talk is Supercharging Tomorrow's Technology with Quantum Physics, and you'll have a better idea of what I mean by that as the talk goes along. So let me start by introducing myself. Javier already started with a brief introduction. I'm from the Department of Chemistry at the University of Alberta, and I'll show you exactly where that is on the map. So here's Canada. Alberta is this yellow province here, and I'm in about halfway up the province, the border. This is the University of Alberta here. And here are two views of our city, Edmonton, in the winter time and in the summertime. So we have quite a cold winter up here in Edmonton. We're fairly north within the country. I think we're the sort of northernmost major city in Canada. Okay, I just want to check. Can you see my cursor, my arrow when I move it around? Okay, perfect. Okay, so that's a little bit about where I'm from. I'm a computational theoretical chemist at the University of Alberta. So let's start very basic. Um, why why talk about batteries to begin with? So as all of you know and have experience, we use batteries every day of our lives. They're in our phones, in our laptops, in electric cars, and backup power units, and the list goes on and on. So batteries play an extremely important role in our lives. And we're always asking for more. We want batteries that are, smaller and lighter, faster to charge, um, longer battery lives. And there are many batteries in existence today, many different types of batteries. Just before the talk, I was talking to another one of the speakers about lithium-ion batteries. And today's batteries, lithium, in particular, lithium-ion batteries are really great. They work very well, but they do have some limits. For example, if we wanted to power a quantum device, a very tiny device, you can't just plug in, a lithium-ion battery into such a quantum device. So there are limits on today's batteries. This is where quantum batteries come in. So with quantum batteries, we're going to explore what happens if we use quantum physics as opposed to electrochemistry to store energy. So let's start with the definition, very basic definition of a battery. So at its core, a battery is simply an energy storage unit. Okay, so what are the functions or the different, let's say, stages of a battery? A battery stores energy. In the case of batteries that we're mostly familiar with, they store chemical energy, electrical energy. And we charge those batteries, so we put energy into them from some other source, and we discharge them when needed. Like, and that simply means taking the energy out to do some work, to power some device, for example. So quantum batteries essentially follow the same idea, but instead of electrochemical cells, we use tiny quantum systems in order to store and discharge energy. So let me give a very, very brief quantum physics refresher. So as I think most of you already know, at very tiny scales on nanometer scales, particles such as atoms, electrons, and other subatomic particles, even light at these scales, behave differently. The rules of physics change at these very microscopic scales. So classical mechanics, the um, the rules of physics that govern macroscopic objects no longer work at these very tiny scales. This is where quantum mechanics comes in. So there are different quantum effects that we can talk about. I'm going to highlight three quantum effects. So these are purely quantum effects. The first that I think some of you or most of you are already familiar with is the concept of quantization. So at this microscopic scale, energy is, let's say, the energy of a system is no longer continuous as at the macroscopic scale. Energy comes in little chunks or little bits. So that's known as quantization. Another important quantum effect is the concept of superposition. So what does superposition mean? It means that a system can be in multiple states at once, at least until a measurement is made on the system. When a measurement is made on the system, that superposition collapses to a single state, one outcome or another. The You may have heard of Schrodinger's thought experiment, Schrodinger's cat. So in Schrodinger's thought experiment, the cat is prepared in a superposition of dead and alive until the box is opened and one checks to see if the cat is dead or alive. Okay, so that's what we mean by a superposition state. And another very important quantum effect is entanglement. So in quantum systems, particles can be linked or correlated even over very large distances, and experiments have shown this, um, such that if you measure one particle or do something to one particle, that there will be an effect on the other entangled particle. Okay, so these three effects are uniquely quantum mechanical in nature, and one would like to exploit these uniquely quantum effects in order to design quantum batteries. Okay, so what is a quantum battery? So the idea of a quantum battery is fairly recent. The first paper on quantum batteries, it was a theoretical paper, was published in 2013. A quantum battery is essentially a quantum system that stores energy. That's basically what a quantum battery is. And the quantum system, I mean, could be really any quantum system. It could be a collection of atoms, could be a collection of molecules, a collection of so-called quantum dots. Basically, any quantum system. Of course, the quantum system has to be designed in just the right way in order to store the energy, which we'll talk about later. And this quantum system will be chargeable. We can put energy into it, store that energy, and then discharge. So from the charging to the storage to the discharge, these are all quantum processes. So this is very different from our let's say our common electrochemical batteries. So what are the main goals in designing a quantum battery? So the first is that we want extremely fast charging. And we're going to talk about that in more detail. We'd like to store energy with very little loss. So we'd like these quantum batteries to be highly energy efficient. And because of their small size, we'd like to be able to integrate them into future quantum technologies and devices. So you may ask the question, why might quantum help? And we already have some idea. So the quantum effects that we talked about, namely quantization, entanglement, and superposition, actually come in very handy. They impart very unique properties to quantum systems. So in terms of charging, these quantum effects and particular quantum correlations and entanglement can allow for something that is known as collective charging. So the basic idea is that many units charge together faster than individually. What we are familiar with is that as you increase the size of the battery, it takes, in general, longer to charge. So, for example, if you have a battery in an electric car, those are quite large batteries. Those may take, 12 hours to charge, for example, versus a battery in your cell phone, which might take 30 minutes to charge. In contrast, in quantum batteries, as you increase the size of the battery, it actually charges more fast. It charges faster. And as I already mentioned, because these batteries are very small, they can enable very compact energy storage at the nanoscale. I should, point out right from the beginning that these quantum batteries are not meant to replace phone batteries or other or laptop batteries and so on, at least not yet, but to explore what's physically possible and fundamentally possible. Okay, so let's contrast classical versus quantum charging. So I'm going to explain the two via an analogy. So charging a classical battery, as on the left here, is like filling, let's say, for example, 100 cups of water, one at a time. So as I said on the previous slide, the larger the battery or the larger the number of cups, the longer it will take to charge the battery. In contrast, in the case of a quantum battery, as is depicted here, those cups are connected or entangled. So it turns out that one can charge them or fill the cups. One could fill the cups using an energy source as a group, as opposed to one by one. So as a result, we can call that type of charging collective, or more technically, entanglement assisted charging. So the larger the number of units in the quantum battery, the faster the charging. And that's a purely quantum mechanical effect. So when people realized this, they got very excited that one could charge, quantum battery extremely fast because of this property. So now I'm going to tell you a bit about our work, the work we've done over the last number of years. So we've worked on a particular type of quantum battery known as an excitonic quantum battery. So these are quantum batteries that store so-called excitons. So let me tell you what an exciton is. I'll use this picture here below to kind of explain the concept. So if one, let's say, has a quantum system with electrons in it, and you shine, let's say, a light or laser light, you can excite that electron to some higher lying electronic state. So here, when you do so, that leaves a hole, a positively charged hole in the ground state, and an excited electron in the excited state. Together, this bound electron hole pair is known as an exciton. And because this excited electron has some energy, you could think of this exciton as a packet of energy. We can move these excitons around in a system. We can discharge them, use them to charge devices or to power devices. So it's a form of, let's say, energy storage in a microscopic system. So they can be formed in molecules and solid state structures. I'll be telling you about some real materials later that one could use to store excitons. So basically, we focused on these excitonic quantum batteries. I'm going to show you how we can store excitons in these batteries, and how they can move. We can move them around and release them on demand. So before I tell you how we actually store the the excitons, I need to introduce the concepts of bright and dark states. So we can use this picture here on the right. So suppose we have some quantum mechanical system with electrons. A bright state of this system is one that one can excite, let's say, using light or a laser. So these upper states here are would be the bright states because I'm able to excite the electron from the ground state to the excited state. And bright states are also able to emit light. So it's easy to lose energy from the bright states through the emission of a photon. In contrast, dark states, like the one shown here, are difficult to excite with light. And similarly, it's difficult for energy to leak out as light, hence the term dark. So the idea that we had is to charge the battery using bright states, so we can access these bright states, but then store the energy in the dark states because it's difficult for energy to leak out as light. And it turns out that many systems have both bright and dark states. I'm going to tell you about a particular setup that allows us to realize that both bright and dark states that are conducive to energy storage. Okay, so how did we accomplish exciton storage in these dark states? So what we found is that if one designs a symmetric network of quantum systems, so such as the one shown here. So in this particular network, we have 6 sites. So you can imagine that at each site, we'd have a quantum system. It could be, again, an atom, a molecule, a quantum dot. And you set up this network in such a way that it exhibits certain symmetries. I'm not going to get into the details, the technical details of those symmetries, but by looking at this, you could sort of see that the network is symmetric. So it turns out that if one designs these symmetric networks of quantum systems, this network will possess both bright states that are good for charging, as we motivated on the previous slide, and dark states that are good for long-term energy storage. And that dark state is actually depicted here in this picture. So you see that, so the dark state in this particular network is, I'm going to use a term that we introduced earlier, a superposition of the systems at sites 2, 3, 5, and 6. So the exciton could be either here, at site 2, 3, 5, and 6. So this dark state does not have any probability at sites 1 and 4. Sites 1 and 4 are coupled to the external environments. Had the dark state had some probability on sites 1 and 4, its energy would leak into the environments. So what we showed is that by charging the system into this dark state, we developed a way to do that, first by exciting the system to a higher lying bright state, and then through natural relaxation processes, the system tends to that dark state, and we showed that the exciton remains there forever under these perfectly symmetric conditions. Of course, in reality, you can never have a perfectly symmetric system, and we'll talk about that a little bit later. But at least under these perfectly symmetric conditions, you can keep the energy there or the exciton there forever. Okay, so that's how we figured out how to store the exciton in this quantum battery. So in addition to storage, we eventually need to discharge the exciton in order to power something. So dark states don't radiate light or photons. So we need to figure out a way how to extract the exciton when it's needed to power something. So we relied on symmetry to create these dark states. So the trick that we use is to break the symmetry now. When you break the symmetry, so for example, by introducing a symmetry breaking environment as shown here. So if you couple this additional environment to sites 2 and 3, you could see that this symmetry, for example, across this axis is broken. So, and another way that we did it is by attaching an exciton sink. So basically another system that extracts the exciton to site 3, which again breaks the symmetry of the battery. So when you do that, it basically turns on pathways that allow the energy or the exciton to flow from the dark states back to the bright states. So what that means is that the energy, which was initially, sorry, the exciton, which was initially localized on sites 2, 3, 5, and 6, can now flow to sites 1 and 4. And then you can imagine attaching other systems to extract the exciton from there. Okay, so what about the robustness of this battery to disorder? So real systems are messy. The positions of the atoms are not perfect. These systems are not perfectly symmetric. There's disorder due to defects, such as shown here on the right. You can have, let's say, static defects. You could also have defects that are induced by heat, by coupling to some environment at a particular temperature. If the temperature is high, that's going to cause the atoms in the system to move a lot. So we have disorder due to both defects and thermal motion in reality. So as you might imagine, that disorder will break the needed symmetry for those so-called symmetry protected dark states. So what disorder does, and we've shown this, is that it reduces the energy storage efficiency of the battery. However, what we also showed is that under realistic levels of disorder, so when the disorder is not overly strong, our dark state strategy that I described to you is surprisingly robust. You still can't store the exciton forever, as in the perfectly symmetric case, but you could store it for, let's say, long enough. For the purposes of powering quantum devices, that might be nanoseconds, that might be milliseconds, um, but depends on the application. But if you make the disorder too strong, then that basically kills the efficiency. Okay, what about some real materials that could be used to construct these systems? So we've been thinking about different materials that could be used. Here are a few examples. So if you picture this 6-site model that I showed you a few slides ago, one could, for example, place quantum dots in just the right way to create a symmetric network at each one of these sites. And the nice thing about quantum dots is they're fairly easy to synthesize, and their sizes are quite tunable. So by changing the size of the quantum dots, you could change the energies or of the excitons that are created at these various sites. So here are a few examples of quantum dots. We're also thinking about using so-called nanographenes. So some of you may have heard of graphene sheets. These are these extended fused carbon ring systems that form sheets. So if we take little pieces or chunks of those graphene sheets, you get what are called nanographenes. And imagine arranging nanographenes on some surface to create a symmetric quantum battery. So that's another idea that we will be pursuing. One could also take crystalline systems such as metal organic frameworks and covalent organic frameworks, which naturally possess a lot of symmetry, and a lot of work has been done about creating excitons in these systems. So an idea we have is to use MOFs, so-called MOFs and COFs, in order to synthesize or design quantum batteries to use them to store excitons. So how do we actually study this? So we are a computational theoretical chemistry group. So we don't do any experiments. We don't synthesize quantum batteries in the lab. We do computational modeling. So essentially, we build models of these quantum batteries. So some of the models that we've built have been more abstract. Others have been more chemically explicit. So we've actually, in a recent study, put anthracene molecules, different size or different anthracene-based molecules at the different sites of the battery. And essentially, we simulate the dynamics of the exciton within the quantum network. So we solve quantum equations of motion for these open quantum systems. So if you recall, the battery is coupled to some environments at some temperatures. And we've also done electronic structure calculations on chemically explicit models in order to parameterize or to input realistic parameters into our models. So what do these simulations allow us to do? Basically, they allow us to explore many designs quickly. Imagine if you had to build all these systems, these quantum batteries in the lab, and imagine if most of those failed, that would be very time consuming and costly, while doing this on a computer is relatively quick and cheap. And after exploring many designs, one could then identify the most promising systems and conditions for the quantum battery, and that will hopefully guide future experiments and experimental groups to then build those quantum batteries. Okay, our research has received actually the our original paper here, which was entitled "Loss-Free Excitonic Quantum Battery," received quite a bit of attention in the media. I'll just show you a few articles that came out in the few years after our paper was published. There's even this one YouTube video with over 1 million views that featured our idea for a loss-free excitonic quantum battery. Actually, just recently, a paper was published in Light Journal, which is a nature-based journal, on March 13th, 2026. And this is really the world's first quantum battery. So all of the ideas that I've talked about have finally come to fruition. In this paper, the authors, it's a group from Australia. Actually, at the conference that Javier was talking about, we met several of the authors at that conference. They demonstrated the first full cycle quantum battery prototype. So this prototype is capable of being charged, it stores energy, and it discharges. In previous works, their experimental works, they did demonstrate charging and some very limited storage. But really, in this one, in this particular work, you could see a picture of the quantum battery here. It's very thin. They actually got current, were able to generate electrical power from this battery. So here's a schematic of the battery itself. It involves many working parts, but the main working material is this copper PC carbon 60, so fullerene buckyballs. That's the working material. That's the material that actually absorbs the light and stores the energy. You can see that each layer of this battery is extremely thin. It's on the order of tens of nanometers, and this is why you see this very thin battery. So they demonstrated actually ultra-fast charging in femtoseconds, which is a quadrillionth or 10 to the minus 15 on the order of 10 to the minus 15 seconds, with energy storage lasting on the order of nanoseconds. So that might not sound like nanosecond is 10 to the minus 9 seconds. That might not sound like a very long time, but like I said, for certain applications, that may be long enough. But for a first demonstration, this was quite amazing. Some potential applications of quantum batteries. So if we can, realize a fully functional quantum battery, they could help with quantum circuits and quantum computers, um, and they could be used in photonic circuits, and molecular electronics, and even in solar energy harvesting by stabilizing those captured excitons. So one would like to store the energy. So the sunlight creates those excitons in these solar cells, and one would like to be able to store those energies, store those excitons in a quantum battery, for example. So just a few potential future applications. Um, I'll say something about the future of quantum energy. So quantum batteries are just a part of a bigger picture. Um, and we're going to be hearing more about quantum computers and quantum communication and quantum sensors today, I believe. All of these things need energy management on very tiny scales, and this is where quantum batteries could really come in. So this is why they could become the powerhouses of future quantum devices. And where could students fit in? So I understand that I'm talking to mainly a high school students and junior undergraduate university students today. So the skills that are involved and to get into this type of research, quantum technology research more generally, physics, in particular quantum physics, um, chemistry, and material science. We eventually need to realize these ideas using real materials, mathematics and computation, for simulations, computer programming, um, and the paths that one could take in order to gain experience in these fields, undergraduate research, whether during summers, in the context of a research course, internships or co-op placements in labs, um, or completing degrees, whether it be in undergrad, grad degrees, in physics, chemistry, and engineering. So the quantum technology field in general is a highly interdisciplinary field, as you could see from the various skills that are required in this field. Okay, before I wrap up, I just want to draw students' attention to a particular award. It's known as the MyTax Global Link Research Award. Actually, one of my new master's students, Alejandra, received this award before joining my group while she was an undergraduate student in Columbia. She took on one of these awards at McMaster University in Ontario. So basically, this Global Link Research Award is meant to give senior undergraduate students and even graduate students the opportunity to carry out 12 to 24 week research internships in a Canadian at a Canadian university. It's a fully paid award, of course, if you receive the award after applying. $6,000 research award to conduct 12 to 24 week research project, or there are even longer internships with higher funding. And I wanted to draw the students' attention, particularly to this quantum stream, um, which is meant for a variety of quantum projects. So students could visit this website for more information, and on the MyTax website, this Canadian organization, you could find a list of all the projects that are available, and one could submit applications for these projects. Okay, and I would like to conclude on that note, thank my group for various members of the group working on the quantum battery research. I'd like to thank Javier for inviting me to give this lecture, the various resources for carrying out this research, and I would like to thank everyone for your attention. Thank you, and I'm happy to take on questions.
Thank you, Gabriel. We are really, really happy to have you here. So yeah, well, so I'm gonna just pick all the different questions that you have. So please post your questions on here on Zoom or YouTube as well. And I'm going to discuss with Professor Hannah. Or if you're here on Zoom and you want to just open your micro, do it please, and you can ask your question. Remember that you can pose your questions on Spanish, in Spanish and also in English. No worries about that. We are going to just make this translation, okay? So, well, somebody is writing, typing here on Zoom. So just give us some minutes, Professor Hannah, please.
Okay.
I have a
So,
question
Yeah.
for
go ahead,
Gabriel.
please.
Yeah, go
Yes,
ahead, Javier.
I brought it in the chatting,
Yeah,
but I think we can discuss this. Thank you very much for your talk. It was very interesting. Was my subject, my preferred subject.
yeah,
And my question is, in classical batteries, normally the charge discharge cycle. At the
yes,
end of this X amount of discharges, the batteries reduce the state of health, and then they are unavailable when
yes.
they break. Is there any equivalent in the quantum battery, something that you, by charging, discharging, you're moving from these different states and moving out of the dark states? And is this degradate as well, or they will be pretty much ever?
I think that would really be material dependent. There might be, let's say, certain materials that one would choose where you would have this degradation over different charge discharge cycles. Um, I don't think the field is quite yet at that point where they're, let's say, I mean, I just showed you one of the first, quantum batteries that was just yeah, published actually a few weeks ago. Um, yeah, in that yeah, I could take a closer look at that paper to see if they experience such an issue. But I would imagine the issue would be there and would be material dependent. Yeah, I would imagine so.
Okay.
But it would manifest itself in a different way than in a classical electrochemical battery.
Okay.
Yeah.
Thank you.
Great. Thank you, Dr. Hannah, and thank you, Julio. So we have probably a question from Monica Vasquez. Please, Monica, open your micro and let us know, or you can type your questions on the meeting chat. Monica. Oh, no, no. No, maybe just she said, yeah, good afternoon. Okay, let's see over YouTube. Some questions. Let's see. Yeah, we have a delay, so probably we should just wait a couple, maybe 1 minute. Sometimes it takes 1 minute. So, but in the meantime, I'm really curious, Dr. Hannah, about the quantum batteries. So, this is not my particular topic, actually, as you know, but I'm curious because we are expecting, or maybe our expectations about quantum computing, those are really high, actually. But what about the quantum batteries? Do you think that maybe in the next decades, or maybe, I don't know, maybe next year, we will have something applicable, or maybe something that we can buy a quantum battery, maybe in stores or something like that?
Yeah, currently I can't see that happening. But what I do see, like for example, I don't think, as I mentioned in my talk, that quantum batteries anytime soon, and I mean over the next few decades, maybe even, can be used to power, let's say, a phone or a laptop. I think really the target applications are going to be, quantum technologies and quantum devices, like for example, yeah, quantum computers. And I seem to recall from the conference that we attended last year in
Yeah.
Italy, they were actually talk. There was one talk where they were proposing an idea for using quantum batteries for powering quantum computers in order, I think it was for stabilizing qubits and quantum computers, something along those lines. So I could see quantum batteries being used for those applications. Um, but as we all know in science, we start with fundamental research and we see what is possible, and then we think about applications and then engineering, how we're going to engineer these devices. But really, the work by the Quach group in Australia was quite amazing. For them to design and get actual power out of these quantum batteries was, I would say, a great first step. I mean, many theoretical papers have been published. There are other ideas. I talked about just dark state sort of based quantum batteries, but there are other ideas out there that could be realized. Um, yeah, but I
Great.
not in the near future for think let's say
Okay.
I can't see us going to Costco or whatever to buy
Yeah, yeah, yeah.
to buy a quantum battery. Yeah.
Okay. Well, so yeah, I have some questions from YouTube as well. So,
Mhm.
it, yeah, Daniela Acosta Miranda, she asked, quantum batteries can support charge in volts, and how many charges could support the quantum batteries in volts?
That's a good question. So I forget the number from, it was small, but from the first the world's first quantum battery, they were able to get I think it was on the order of nanovolts. I forget the number, but it was
Okay.
small. It was a small amount of voltage. Um, but like I said, it was an initial demonstration. Yeah, I can probably take a look at the paper.
Okay.
But yeah, maybe later on I can find that number
Mm.
and report that number. But it was a
Yeah.
small voltage.
It is
Yeah.
small. So, well, so what is the challenge part about that? So, in terms of the voltage, do you mean maybe the engineering part, or maybe what is
I think
the
I think
part?
scaling these batteries up. So
Oh,
yeah,
great. Okay, okay.
it's the
Got it.
number of let's say absorbers
Got
uh,
it.
in the battery. So
Great.
one could increase the amount of, let's say, uh, active material and scale up the size that way.
Got it.
So
Okay.
yeah, I think that's one of the big challenges, scaling
Okay,
up the
okay.
size of the batteries.
Yeah, but if we want to increase the size of the batteries, we will need a particular kind of material, right? I don't know, maybe
E, uh,
such to yeah.
yeah, like one of the ideas that I had, so I mentioned this quantum dot based um, quantum battery. So the idea that I had was to use, let's say, I didn't show a picture, but to use some, let's say, nano lithography technique and put down quantum dots on like in like many quantum dots. I don't know, like thousands of quantum dots in a particular like in on a surface, like in a structured array. And and
Oh,
and yeah, I would like start small to test the idea, but the I let's say the idea that I have would be to basically design a large array or fabricate a large array of these quantum dots in with just the right symmetry and and um, and go from there. But you would need many uh, quantum dots to
oh,
increase
got it.
the power
Okay.
output. Yeah.
Yeah, this is
But
pretty. I'm sorry. Go ahead. Sorry, Dr. Hannah.
yeah, no, that's basically all. You need many units. Yeah, many units to accomplish that.
Oh,
Yeah, to
okay.
get. So this is why I see, at least for the time being, these these quantum batteries being used for just quantum technologies where the amount of, let's say, power isn't going to be that much, that 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 large.
Okay. Okay. So, well, so just one more question, I think so. Yeah, we have more questions, but I think maybe a couple of questions. And the next one is, what are the key research areas of opportunity? Well, Monica asked about the quantum computer, but I think maybe quantum energy or quantum batteries for the 2026. So the question again is, what are the key research areas of opportunity in quantum batteries for 2026? Do you
Yeah,
think?
I think quantum batteries fall under the larger umbrella of quantum technologies. So I think um, like quantum energy for quantum computing, quantum energy for quantum communication, sensors. Um, I think those are sort of those might be the near term uh, applications of quantum batteries. Yeah.
Okay. And yeah, this is the last one. And Natalia said, how can I re-enter the world quantum of, sorry, so how can I re-enter the world of quantum mechanics if I have a bachelor's in engineering physics? But right now I am in the field of data science and analysis. What would be
Yeah.
the strategic steps?
So if what I missed the name. What was the name?
Natalia.
Natalia. Yeah, if
Yeah.
Natalia has a degree, an undergraduate degree in engineering physics, I think that's a
Yes.
very solid foundation. I don't know how much quantum mechanics Natalia has learned. I think here in engineering physics they do learn a bit of quantum mechanics, but I think maybe a good stepping stone might be a master's in for example, theoretical computational chemistry, or in physics, a master. Like I think maybe going from engineering physics to physics might be a natural path forward. So using like a master's degree as a stepping stone to learn more quantum mechanics through course-based work and research, and then moving on from there onto a PhD if Natalia desires. I think that might be a good path forward.
Okay. Thank you, Dr.
Yeah.
Hannah. So yeah, but thank you guys for all these different questions. And also, Dr. Gary Hannah, we appreciate your time. We really, really are happy that you to be here. And we are going just to continue with the next session, next part. And but if you want to stay with us, so should be really
I'll be
good.
staying. Yeah.
Otherwise,
Thank you, Javier.
yeah, thank you. And then we are going to keep in touch, okay?
Yeah, sounds good. Thank you, Javier. Yeah, I'll
Thank you so
stick around.
much.
Yeah, I'll be here.
Bye bye. Okay. For everyone, guys, thank you for joining us. We see people from Peru, Colombia, Canada. So please feel free to put your questions, all of this on Zoom, maybe YouTube if you are here. And we are gonna move forward with the next part of the sessions for today. Remember, you can pose your questions in Spanish or in English. Don't be shy, please. Um, let's see, I'm trying to find what is my I have a tons of tabs, so sorry. I tried to follow all of this. So well, now in Spanish, we are going to switch to Spanish with Dr. Julio Gonzalez, and also with me. So, well, now in Spanish. Guys, muchachos, gracias a todos por unirse aquí por Zoom, también los que están en YouTube. De verdad que este es un esfuerzo de la comunidad de la facultad, de la UNAM, de profesores internacionales, de investigadores de diferentes países que con los que hemos conectado desde QMexico, también desde Caldas, algunos de ellos pues hablan en español, otros en inglés. No se sientan, por favor, cohibidos si quieren preguntar en inglés o en español, háganlo, por favor. La idea con este evento es tener, cubrir tópicos muy básicos, pero también encontrar muchos tecnicismos. No se sientan, por favor, para nada cohibidos, ¿ok? Bueno, ahora vamos a estar hablando en español, en inglés, porque la verdad no sabemos cuántos tenemos con idioma nativo en inglés, pero por favor, no se preocupen, solamente abran su micrófono si tienen la opción aquí en Zoom. Pregúntenos en español, pregúntenos en inglés y vamos a empezar con la sesión con el doctor Julio González, ¿ok? Bueno, okay, so we are going to start in English. Sounds good. Just to follow all these different sessions. So welcome, Dr. Julio González. Thank you for joining us, Doctor.
Oh, thank you very much, Javier. Thank you very much for having me here. It's very exciting, especially the Gabriel conversation. This is one of my favorite topics. I did my research in batteries, but the classical one, and I was very surprised when he mentioned the same battery topics, and then it's getting miniaturized and getting very small to the quantum. Thank you very much for having me here. Thank you.
No, we're happy, really happy to speak with all of you. I know Dr. Julio Gonzalez. He's actually, let me introduce him. I'm sorry about that. Yeah, Dr. Julio Gonzalez is a quantum promoter at Vodafone with a leadership focus on modern engineering practices in quantum safe security. He oversees initiatives that help teams assess cryptographic exposure, transition toward quantum resilient architectures, and integrate emerging technologies into long-term strategy. His area of research is application of quantum computing to solve energy optimization problems, bringing a forward-looking perspective that connects advanced research with practical engineering research leaderships. So, yeah, Dr. Julio Gonzalez, as I just read, he's working at Vodafone, and he's working in London, right, Dr.
Yes.
Gonzalez?
Yep.
Yeah. So would you like to start with any particular topic?
Yeah.
This session, sorry, just a minute. This session, it's like a panel. So we are going to, or a kind of conversation. So we are going to talk with Dr. Gonzalez. So please open your chat box and put all the different questions. We are going to try to cover different areas or different fields in quantum computing, quantum energy, quantum batteries, quantum cryptography, quantum machine learning, actually. So just put your question. We are not going probably to know all the different topics, but we will try to cover or to answer your questions, okay? So, well, Go
Okay.
ahead, Dr.
Okay,
Gonzalez.
let me share one to put some context. I will share my screen. Share. Where is this one? Share. You see my screen?
Yes.
Okay,
Yeah,
good.
we do.
Okay. This conversation was born because we think the students now leaving the high school and getting into higher education now they are in a situation that said, which path do I follow? If they are non-technical people, then they will know more or less what follow. But when they are technical people, there are so many areas now, very important areas, and most of the times the decisions are based on how much the technology will be mature soon, because everyone wants a nice work, well paid, with good benefits. And then I say, if you pick the right technology path, then you will be in that area. If you pick the wrong technology path, you might be uh, having some issues later. Then the idea is what we can tell, what can discuss with the new generation about quantum computing. It makes sense to study quantum computing. It's just a hype. This is just saying, yeah, quantum computing, and then everybody's happy. And then 2, 3 years later, nothing happened, and then you invest a huge amount of time and money trying to discover the quantum mechanics and understand this, and then you say, "Well, why I did it." This is the idea, to instigate the discussion. Does it make sense to get into quantum, or really it's better another technology that will be faster into the market? You get a job faster, and then you will start getting benefits from your work, from your study. But then I said, okay, this is how mature is the field. Is it really mature? Does it make sense to study now quantum and then get something immediately? Then I prepared 2 slides, and I say I will just compare things together. And then for young people watching this video or this conversation, it's just open eyes. No, this is the idea: is open eyes, provide some evidence what's going on, and then eventually you will decide your future. No, this is you will the only responsible to pick the right path. Then what I did is that I call this from Moore's law to quantum computing. Uh, Let me put it here. I start my studies in 1982, which means I am 44 years in the market. I've been working in telecommunications since 82, which means I have seen the telecommunication, the computer industry growing from the get-go. That means this is my point. This is, I have a lot of years working in this area. Then you will see that it's not just I study this and tomorrow I will start making a lot of money. It takes a while, and then that's why I want to present these two slides. This one, that's the first one. On the left-hand side, you see that the Moore's law. It started in 1970, and then you can see the scale of the number of transistor in the package. Initially, you cannot even see the values. Then from 1970 to 2020, there was 50 years since Moore law started until we really start getting some tracking. 50 years. Then you will say, okay, I started in 1980, which means I picked the right one, because now 50 years later, I Moore's law said, that's it. That's this nothing we can do more. 2020, 2023, Moore's law, stop. You cannot double the size of transistors in the package. It's impossible now. The limitation is size, and you're putting now the transistors so many together that now the whole effect between atoms is really, really bad. Then on the right-hand side, I have the technology of qubits. You can see everything started around 2000. In 2000, they started the same thing, 2000, the number of qubits are really, really small. And you can see in 2035, 2040, then things according to the industry, and all this information comes from the many vendors of quantum computers. This is by 2040, you will start seeing what we see now in the Moore's law. But of course, quantum can evolve much faster, much bigger, sorry, not faster, bigger, which means you can now check 40 years later, not from 2020, 2000 to 2040, is 40 years, which is the same pretty much the Moore's law. And then if you see the other technology in quantum, the quantum annealing, similar thing. It's a different technology, always in quantum, but the technology is a little bit different. But you can see the same tendency. Starting 2010, this is D-Wave, as Javier mentioned. D-Wave started in 2010 before, but they really started producing in 2010. And they expect by 2040 having around 1 million qubits. Then you see same thing, 40 years later, you will start getting traction, which means if you start like I started in the 40s, now I have a lot of experience. I pick the right choice, and then I would say I'm happy with what I select, because now in quantum is you use a comparison. That's the one thing. Now let me show this one, the second one. On the left-hand side, you see ENIAC. Everybody probably is not, if you're not familiar with ENIAC, ENIAC was the first electronic computer board in around 1945, 1950s. Was made out of tubes, and this was 3-4 bits, something like this, of information. Huge amount of equipment, lots of equipment, lots of equipment. And then you say, now people say, oh yeah, but quantum computing is huge, it's a big thing. You see the announcements, and you can see very clear Javier picture on the background. You can see a quantum computer. This is a traditional picture of an IBM quantum computer. You can see the refrigerator. You can see at the end of this, you will see the quantum chip. What you see on the top, this is only a refrigerator to make things. Yeah, exactly. Yeah, this is only to keep the computer cool. The chip is at the end of this. It's a little chip that is there. But this is what they said. But you see in the lab, this is this is a real lab. Yeah, this I gave the reference there. This is an experiment in quantum computing. You see, it's not as a nice, clean thing. You see, it's a lot of the complexity of the experiments are still heavy. There's some computers that are working. I'm not saying all the quantum computers are like this, but it means my point is quantum computing is still in the infancy. Still, there is a lot of things to do. There are many technologies, as Javier mentioned, superconducting, quantum annealing, quantum dots, as Professor Hanna said. We have also neutral atoms. There are many, many different technologies. Who knows who's going to win the race? There is no clear picture now. This is a supercomputers, I'm sorry, superconducting qubits or optic photonics. There's no clear view. The market says there are chances that there will be different vendors for different applications. Not like we have here laptop. You have your laptop and you work in healthcare, you use your laptop. You want to engineering, you want to build a bridge, you use a laptop. Is similar, is the same equipment. In the quantum computing will be different. There will be a specific machines dedicated to specific problems, and there will be maybe a fault tolerant machine that handles many problems, common problems like quantum machine learning and energy optimization problems. Those things maybe is specific fault tolerant, but the race is still not clear. This is nobody knows who's going to win. IBM, Google, Microsoft, Amazon, PsiQuantum, Quantinuum, those are big companies, huge amount of money invested, but still the race is on. This is no clear picture. And the last picture I want to show is this is a investment. It's just to show you that the technology is backed up with a huge amount of money from countries, enormous amount of money. For example, I live here in the UK. So the country has invested so far 4 billion, more than 4 billion US dollars in technologies, and still investing. We want in the UK, we want to be in 2035, I think. There is a vision from the government saying by 2035, they want to build the first quantum company. They call it the trillion economy, which means they expect the economy, this company like Apple, the value is $1 trillion working in quantum, which means the technology is backup. Is definitely there is a huge amount of money invest. It makes sense to get some of this money for the mainly research. There's nothing yet that we can say is a huge amount of companies selling real quantum computers. Those you see, there's research. Everywhere you go, their research. Unfortunately, Latin America is a little bit behind, but it's a different story. Like Africa, I personally believe that the reason is not because we don't want to invest, is because probably we are waiting. Because instead of investing money in something that maybe will, let's say, Mexico, for example, takes superconducting, just an example, because it's clear it's the first country. Uh, um, Nothing specific, but just Mexico. They pick superconducting, for example, and the technology is neutral atom, then all the money invested it is destroyed, it's not used. Then it's better to wait a little bit, not much, but it's good to wait to invest in the technology, but not to start catching up with technology. This is what I want to say and to put it in the context. Now, Javier, I think as a recommendation for our young students, I just have an anecdote. When I did my master degree, I did it in computer science. There was my professor. It was in 2004, 2002. My professor put me in path. Said there is a DNA computing here, and there is a quantum computer. Which one you want to study to do your master? And I say, cool is quantum is a DNA computing. DNA is cool, sounds familiar, sounds biology, chemistry, very nice. And I pick that route. 3 years later, the technology disappeared. I mean, it, it proves that you have to no you pick your path based on the information you have. What you need to do is really inform yourself very good what opportunities are, and it doesn't don't think that tomorrow you will be a huge in a big salary uh, job. It takes a while. It takes really a while to get in the technology. But if you start now, you will see 30, 40 years later, guarantee that this will work. Mm. This is my presentation now. You want to discuss something to help the young engineers or young high schoolers, we can start.
Of course, yeah. So, well, guys, so everybody, please post your questions right now, comments, or any kind of feedback, please. Well, I have question just to uh, connect with your first, no, sorry, second slide, which is about the Moore's law. So, I would like to just bring the people attention about this interesting law. This is so. I mean, I would like to know why this is important. This kind of law is very important, and I'm saying this because some people could say that this is not actually currently a law that the technology is following. And this is because we have currently this quantum computing, which is the idea with the quantum computing is try to reduce all the different devices. But when we do that, then the 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 physical laws and also the how we can say probably particles that we are using to transmit the information are going to interact those two between each other, right? So in other words, if we construct a small device, this device will have electrons, positrons, and other different particles, but when we are transmitting information, this also has some voltage or probably currents done where those currents are going to interact each other with the particles in our material, right? So this is why some people probably say that the Moore's law doesn't follow currently, but this was very important. This law in decades 18, I think so, was when
Yes,
Moore
because exactly. This is a very good point, Javier, because this is if somebody wants to go with classical now, let's say I want to study classical, eventually the semiconductor reach the maximal amount of transistors. That means they will stay what is the current situation. They will cannot be improved because now if they put more, electrons will touch each other.
right.
And then it won't work. That means we need to move to a different technology, whatever technology is. But of course, what we are we are thinking is quantum will be the recommendation to study, not the study the classical hardware, because this yeah, we can say yes, but I want a job in 2 years. Okay, then it's true. In 2 years, FPGAs, for example, we are using for controlling qubits. We use FPGAs, and FPGAs are improving. You know, I think NVIDIA defines the GPUs and NVIDIA and this FPGAs, but they will be eventually limited. They have to move into the quantum, and then students or young engineers, young students, they have to start thinking in not in the 2 years time frame, but a little bit longer.
Yeah, yeah, correct. So what? So yeah, so that's why we are talking about this, guys, in and our dear audience, Karen, that we have on Zoom and also on YouTube. It is important because it's a time where we are we have to think what the technology what is the next step up of the technology, right? And also when we create and when we develop technology, uh, maybe we don't think about that, but when the technology pushes, there was previously science such as physics, chemistry, math, biology, and where another kind of sciences uh, that pushes this technology. And currently, we are just talking about this Moore's law, which was proposed in more kind of 40 years ago. And then we are thinking that, well, what happens with technology, particularly with quantum computing and also quantum batteries, quantum cryptography, right? And then behind this, we also have some different concepts, fundamental concepts, some of them coming from physics, some of them coming from math. Okay, so part with this particular with this talk is try to bring all these different concepts. Dr. Gonzalez, I think it was really good idea to mention about the Moore's law because it was one uh, important law or concept when Morse proposed that and said or analyzed how this transistor size were growing or changing with the time, right?
Mhm.
So, well, so that's why it's very important and interesting. So I'm going to show you in next probably and some minutes later, I'm going to show you some details about this or similar about this. Okay. So, well, let's see if there are more questions on Zoom. Please, guys, pause. Oh, there is one. I'm sorry, I was missing some of them. I was really excited talking about this. Sorry. Let's see. Okay, so this is going to be in Spanish. So, dice, con background teórico en tecnologías cuánticas, pero sin experiencia experimental, se puede aspirar a trabajar en la industria de las tecnologías cuánticas. So, if you want,
Okay.
we can talk about this in Spanish or in English, Dr.
Okay.
Gonzalez.
I don't know, maybe because the question was in Spanish, or I will answer in Spanish. No es necesario, yo soy ingeniero en Vodafone, donde yo trabajo. No hay físicos experimentales. La idea no es traer un físico a que haga un trabajo. La idea es proveer un servicio en el que no se requiera una gran cantidad de academia, sino que se te tenga mucho entusiasmo, mucho nivel de curiosidad, que sea un poco terco, un poco terco en el sentido de no me salió, pues lo intento otra vez, y no me salió y lo intento otra vez, en lugar de decir no me salió, lo tiro, ¿no? Eso es terquedad en el buen sentido. eh, Prácticamente si quieres una universidad, entonces ahí sí, porque ahí un trabajo experimental es, tiene más para la industria, porque la industria requiere mucha experimentación. Y para hacer esos experimentos no es fácil hacerlos. Como viste, la complejidad de los equipos es mucha. Pero para iniciar el trabajo, no es necesario ni siquiera un doctorado en física. En Vodafone nosotros tenemos dos ingenieros, bueno, un matemático, una persona que tiene un bachelor en matemática y un master degree en física. Ellos son parte del grupo de Quantum. Claro, el director de Quantum del grupo es físico, él sí es físico, pero las personas que están trabajando el día a día no son físicos, yo no soy físico, yo soy ingeniero y tengo abierto el campo a estudiar. No todavía un trabajo fijo que uno diga puedo conseguir en hacer una mecánica cuántica, pero un trabajo con una computadora cuántica, eso todavía está lejos, un poco lejos, pero se puede probar. Hay muchas ayudas en el Internet, hay simuladores en el que simulan exactamente una computadora cuántica, los principios cuánticos. No es necesario, como decía el profesor Hanna, para estudiar eso se hace en la computadora, no es necesario construir la computadora y probar en la computadora, se hace en los simuladores y es exactamente igual que tener una computadora cuántica.
Efectivamente, eso es. Espérame, a ver si hay más. Oh, yeah, there is one more. And we are going to just follow your comment of maybe a question, one more question from Alejandra. Or if you think that maybe we need to clarify some topics, let us know, please. So the second question is quantum or AI? What's your hot take on these technologies? What do you
Okay,
think, Dr. Gonzalez?
favorite subject. Um, Currently, my job in Vodafone, part of this is working in the artificial intelligence. We have a lot of interest in artificial intelligence in all the products. Everything is pretty much now AI. However, there is a branch in the quantum computing called quantum machine learning. If you are familiar with machine learning, what it is you grab a lot of data, pass it through an optimization algorithm, and then you obtain an output. But what happened is this optimization algorithm is being replaced with a quantum algorithm. I mean, you have the classical computer, the classical part of the the machine learning, but instead of sending to, for example, PyTorch to develop to the network, the quantum network, sorry, the neural network, what it does is uses a quantum algorithm to estimate the new the optimization, and then takes this optimized stuff, and then feed it into the quantum, into the neural network, and then do the artificial intelligence. That means this is the next big thing, artificial intelligence and quantum. They will be together. I think this will be the first real application that will be in the market. There is a lot of application that uh, um, Javier mentioned, but the quantum machine learning is understandable by everyone. Everyone understand what is machine learning, and the quantum part is just the optimization algorithm, which means if you study both, then guarantee job in the next decade, definitely.
Yeah, so, well, let's see. Yeah, Alejandra said gracias. And how about Natalia? Natalia asked about the quantum or AI. What's your hot take on these technologies? So, Natalia, please let us know if you want to follow this question. And let's see on Zoom. So, do you have any question, guys? Please open your micro if you want. Let us know. We have some people here.
Maybe a little bit to clarify something with the machine learning. In Vodafone, as a telecom company, we control the fraud. This is a fraud is a lot of uh, problems in a telecom company. Then we use artificial intelligence now to detect fraud. This is if a call is valid or not. But the issue with this is you have a small amount of parameter you can measure, because it's so many things, and the volume is so high that you can measure a little bit of parameters to estimate the fraud. And we are trying to introduce machine learning, quantum machine learning in the algorithm, so that instead of having 3, 4 parameters to detect a fraud, we can use up to 100 parameters. And then you can really grain the fraud and detect fraud that before you could not detect. And in this, we have estimated that in 5 years, we can save $100 million. You can improve the fraud detection for 10%. $100 million in 5 years. This is data from our company. That means quantum machine learning is getting a lot of traction, and this will be if you study this too, you don't need to be a genius. You just study this, grab the concept, and that's it. Guarantee a job.
Sorry, I was mute. It's okay. Yeah, thank you, Dr. Gonzalez. So let's see. Well, yeah, they say very interesting. So I have a question, and just thinking about our next generation of scientists, because we know there are a lot of different people motivated about this kind of technologies. But my question is, how, thinking as a Latin American guy in the future, how we can contribute in our countries to promote this kind of technologies. Probably, I don't know, talking about this in at the universities, or maybe try to bring those topics with the, I don't know, different leaders, probably government, probably different companies. I think that should be one good point to start. But what do you think, Dr. Gonzalez?
Yes, as I mentioned in the slide about investing, Latin America is a little bit behind. It's um, we believe that it's because we are waiting. That's my point. My view is we are waiting for this technology to mature. and the political arena is not yet prepared, because this is something that if you do wrong, you will have to invest a lot of money and then waste the money, and then this will be a political price you have to pay. I think it's it's coming, because there is no way they eventually will have to do it. There is no in 5-10 years, what happened is a quantum computer will break security, and then everybody will be exposed to cyber attacks. That means big countries now are improving their networks to protect to these type of attacks in the next 5 years. And if we are behind, that means our economies will be compromised, the sovereignty of the country will be compromised, secrets of the country will be compromised. Then this is already there, and sooner or later, Latin America will have to. It's not the question is not if, but is when, because it will. And if they leave this for long, the vulnerabilities for those things will be tremendously expensive for the industry, for financial, healthcare, blockchain, bitcoins. Everything is unprotected. I mean, we will have big troubles if we don't act quickly and organized, because it's not just we have to change now to protect our things for a quantum computer. No, you need a lot of time to prepare for this change. And quantum computers, the problem, there's good guys and bad guys. The good guys, they show off what they have. No, we have 100 bits, 100 qubits. The bad guys, they don't show. They just execute, and when they have a computer before the good guys, then they will start doing really bad things to the good guys. Then that means the good guys has to be faster than the bad guys. Now, who are the bad guys? Who are the good guys? I leave it to you. This is uh, I don't know who is good and who is bad. I cannot define this, but what I'm saying is whoever is considered bad, they will not say, I have a quantum computer, I will start decoding. And whoever is good, they will say, yes, I found the computer, then I will protect. This is Latin America, Javier, to answer your question, we must act very quickly.
Yes, I think so. I agree. Totally agree. So, well, we have two more interesting questions actually. Well, we have probably more, but people don't post the questions on the chat box. But well, let me read one of these. It says, uh, Dr. Gabriel Hanna has one interesting question, and also Alejandra. Okay. Let's see. Dr. Gavin Hanna asks, thank you for your great overview. I have a question related to the scalability of qubits in quantum computers. What are the main technical challenges to increasing the number of qubits?
Yeah, yes. The big issue, Dr. Hanna, is error correction. That's the big problem. There's still the error correction. There's a lot of high in the literature evidence that show, oh, we have a breakthrough in the error correction. Now we are reducing that we can produce millions of qubits. Currently, I think there's not a big problem producing millions of qubits, but all these millions of qubits will be the coherence time will be extremely bad, and they will immediately lose the state, which means they are worthless. That means we have now, I think the most is 160 qubits, logical qubits, and this is what we measure, the logical qubits, and it's going very slowly. The scalability, once people discover a real error correction algorithm that works, this is when scalability, there is no limit, because making a qubit is relatively simple. As you mentioned, dot atom dot the dots, those are really simple, just manage how they put it into the matrix. But if you make them really useful, they maintain the coherence and the state so that you can process them, then it will be fine. But still, it's a long way, long way.
Yeah, one of the reasons why I asked that question is because I recently came across a news article. I think it was a startup company in Israel was claiming that they will be able to build a quantum computer, a neutral atom-based quantum computer with millions of qubits. Um, and as you pointed out, like we're hearing about computers with like less than 1,000 qubits, so there's a big, gap
Yes.
there. So I was wondering,
Yeah.
yeah, what the main technical challenges are. But yeah,
Uh,
error correction.
yes, that's
Yeah,
the
sounds
big issue, because currently I think you have, for each logical qubit you use 100 or 1,000 bits qubits, which means you want to put 100 uh, logical qubits, you will need like 100,000 qubits, and with 100 qubits you do nothing. This is there's no classical, not improving for the classical way. You need at least to break RSA. They say we need 100,000. I think they say 100,000 logical qubits. You want to break RSA, and the predictions are that in 5 years RSA will be broken. It's because they think that error correction will be improving, not because you will add more qubits. It's because now you can keep the coherence time much time, and then you can decode a key in 7 minutes. I think that's the last algorithm, that the paper published by Google by at the end of March. They discovered this algorithm that 100,000 logical qubits can decode a key in 7 minutes. I mean, but to get to this point, the industry says 5 years. 2029 is the US government mandates that all federal agents change the encryption to the new phase quantum safe algorithms, because they think by 2029 somebody will have a quantum computer able to break RSA and ECC.
thank you.
Yeah, thank you, Dr. Hanna. So, and thank you, Dr. Gonzalez. I would like to add something that actually you mentioned, which is about the coherence. It is because we will mention previously that the qubits are extremely fragile, right? Remember that we mentioned that uh, we have qubits probably interactive with the environment, right?
Mhm.
Actually, with the mediums, with the devices. So that's about the coherence, and also the other important. Those two important topics are the quantum error correction. Those two are very challenges topics in the industry currently. So yeah,
Yes.
thank you so much. We appreciate. Let me see. We have some more questions. Uh, yeah, Ivan asks, quantum computers are currently expensive due to the cooling requirements, but we will have room temperature computers at some point to make them more scalable. How long might that take?
Yes, this is the computer that Javier shows. This is superconducting, and I think there's another technology. I forgot they use a this delusional refrigerator. Not all technologies are that way. For example, photonics, you have ambient temperature. In photonics, you don't need cooling to do this um, the quantum computer. You don't. It's you do it to a room temperature, and the thing is, they are very complicated devices. It's not the what they have to do is reduce all these lasers and things that they use to control the optics to things that really are small. But as I show you in the picture, this one, this is the picture of an experiment in optic photonics. Is ambient temperature. Here they are manipulating qubits using lasers. Here, that means it is ambient temperature. They are expensive because they are very complex. Imagine lasers. You have to count photons, not single photons, to get this working. And you need to count a single photon. And I was in an experiment. And then even we were measuring the photons, and then the device measured one single photon, but the ambient light, we covered the device, the measured device, with black sheets, and we put it very covered. Light cannot enter, and we never get one single photon. We always get 200, 300, because even is completely protected. It's so sensitive that is a little bit of one extra photon will change the qubit. I mean, this is why they're expensive. The cooling is really, yeah, it's expensive, but also the superconducting technology is, you need, this junction has to be very stable. You cannot have interference or things, and one electron doing something that they should not. Why you have to avoid those. Yeah, but that's the reason are expensive. It's not because they are actually cryogenic. It's because they are really complex, and all of them are expensive because they are clever devices that's still under development.
Great. Thank you, Dr. Julio. Well, so let's see, more questions. Maybe some people wants to pose more questions. We have a same question, but now in Spanish from Ivan Barrientos. But it's the same one. I'm going to read just to follow these questions in Spanish, okay? So, actualmente las computadoras cuánticas son caras por la refrigeración, pero tendremos computadoras a temperatura ambiente en algún momento para que sean más escalables. ¿Y cuánto tiempo podría tomarnos? ¿Ok? Fue la pregunta en español. Solamente para darle seguimiento, por favor déjenos saber si hemos respondido, si quieren que les demos alguna otra perspectiva de las preguntas, de las ideas que se han propuesto, de los conceptos que se han expuesto también. No teman, por favor, posteen sus preguntas. Déjenme ver si hay más por aquí por Zoom. Okay. Well, so it seems that we don't have more questions currently. And again, we have a delay, so maybe we have to wait just 1 or 2 minutes in case somebody wants to post some questions, some additional questions. So thank you, Dr. Gonzalez. So in the meantime,
Pleasure.
Sorry. Sorry, go ahead.
No, my pleasure, Javier.
Thank you. Thank you so much. Well, so I would like just to, in meantime, just to maybe to wait for a while. Dr. Julio Gonzalez and I, with more people from Central America and also South America, and actually here in Mexico, we are working on on one particular initiative, right? So this is in the future. We would like to people, all of you, follow probably our social media. Dr. Gonzalez, if you want to post your social media here in the chat box, in meeting chat in Zoom, you can do it, and I'm going to share with people on YouTube. And same for Dr. Gabriel Hanna. If you want to share with us your social media, you can just post here on Zoom, and I'm going to share with people on YouTube. But actually, guys, all of you can find all of us, Dr. Gabriel Hanna, Dr. Julio Gonzalez, and I, in I am in Google Scholar. You can just post it over there. This is Dr. Julio Gonzalez. You can follow him. If you want to ask anything else, just please do it. And I'm gonna post as well my website. Not right now, maybe later. But well, so you can find us. We have different papers about quantum computing, quantum batteries, quantum machine learning. You know about Dr. Julio Gonzalez. He also have his profile in he has his profile in Ocular. It is I posted the website on YouTube, and also you can find here in the meeting chat on Zoom. Well, so okay, okay, Dr. Gonzalez. Oh, let's see. Oh yeah, Dr. Gabriel Hanna said, I'm working on updating my website, which should be completed in near future. Okay, so he's working on his website. Um, but well, so if you want, you can just email us as well, or find our profiles on social media, different such as LinkedIn, X, and probably others about science, right? Google Scholar is another one. Well, so Dr. Gonzalez, would you like to add something just to close this
Yeah.
part, this talk?
Yes, I would like a message for the younger people. It's we are now in the inflection, I wouldn't say inflection point, at the starting point, like we were 40 years, 50 years ago. I mean, it's the technology has a lot of promises. It's similar in the 70s when people say, ah, do I need to join the computer science or not? And then people know they use civil engineering and other things. But some people selected electronic engineer, and now we are with the technology. Now we are going out the technology. Now this is our time is pretty much over. This is um, because the technology, classic technology, is pretty much not dying, but will not evolve. Now it's time to jump into the quantum technology. And this is what I did. I jump into the quantum technology and I start growing with the quantum technology. You can start, there is 1,000 of places you can learn. Now the quantum computer is democratized. You don't need anyone. You don't need even to go to university. You have a chat GPT, Claude. You can learn. You can ask Claude, give me a curriculum, give me the classes. You can find books all over the world, all over the internet. There are free books. There's a lot of help. There is a stack chain exchange that you can dedicate it to quantum. There is a lot of resources that if you want to learn, there is no limit. It's just to decide, I want to do this, and then go ahead, go for it. But of course, you can decide, no, it's too much work. That's fine as well. But eventually, it will pay off later, but you have to invest time. And but I say, it's so democratized that you can find everything pretty much for free. Pretty much, you Coursera, the Allison, LinkedIn. There's so many places you can find help. ChatGPT, Claude, Gemini is free. They have a Gemini Flash 2.5. It's an excellent tool to learn. I say IBM. You register to IBM, and you can even use a real quantum computing for 10 minutes for free a month. That means there is no limit. Is if you want to learn, you cannot say, oh, I don't have the skills and all. You have the skills. If you don't have it, you can get them. But the only thing you need is, yeah, ganas, and that's it. That's my message. Go ahead, guys. If you want to study, the technology is really amazing. It's a it's not complex. Maybe if you want to do physics, that's a different story. But you want to do engineering, you want to do development, you want to do practical things, forget it. The study in a PhD in physics, you just need a PhD maybe in engineering and electrical engineering or quantum computing. That there's a lot of universities that start providing similar curriculums and on that subject. Yeah, that's my message, Javier, and thank you very much for the invitation.
Thank you, Dr. Julio Gonzalez. We appreciate your time. Thank you again. We really, really enjoyed this conversation. Let's see, just maybe if somebody wants to add anything else on YouTube. No, we don't have anything. And about yeah, in Zoom, people say thank you so much. Uh, okay, so okay, let's see. I have a message from. Okay, no, I think everything is okay. Are you aware? Let's see. Wait, second.
Yeah, there is a
wait.
question for you.
Yeah, there is one more.
Yes, there's a question for you. Jordan.
Uh, yeah, Jordan Janonin. Are you aware of any quantum initiatives planned for Mexico, Central America, or South America? Yeah, South America. Yes, we are working on that with Dr. Gonzalez and more people. We will post this soon. Soon, I think so. Um, but yes, that's why we mentioned about our social media. Please pay attention in our social media. Dr. Julio Gonzalez posted here his website, and also I posted on YouTube. And I posted my website on YouTube, and I'm gonna do that here as well. Okay. So thank you so much, guys. This is our session with Dr. Julio Gonzalez Science. We are going to talk about now it's my turn at 4 p.m. We are going to start. So we are going just to close for 4 minutes, and we are going to start at minutes right now. And at 4 p.m. we are going to start again. Okay. Oh, this is social media. Dr. Julio Gonzalez.
Yeah,
I'm
this
going
is
to post as well. Sorry, go ahead.
that's thank you, Javier. I have to leave because I have another meeting in 4 minutes. Then was very nice, was very interesting conversation, and we will have to participate. Or if you have any questions, you can julio.gonzalez@inoc.com. It's my email. Then just send questions, and I will be really happy to answer and give you real examples of real applications that we are doing at Vodafone.
Thank you, Dr. Gonzalez. So have a
Okay,
rest of the night for you, and thank you so much. We will
thank you
keep in
very
touch.
much. Yep,
Thank you. Bye.
thank you. Bye bye.
Okay, so for all of you, well, we have 2 more minutes, and we are going to uh, just stretch our legs for 2 minutes, and we will be back in 2 minutes. Okay, just 2 minutes. Thank you. Okay, so yeah, thank you so much for being here, guys, again, and thank you, everybody. Just let me make sure that you can hear me on YouTube. Let's see. I need to check my slides. Yeah, so I'm gonna share my slides right now. And please just let me know that you are able to see. Um, let's see. Let's see. Let's see what is okay. Um, okay. What is, oh, sorry, second, because I don't see what is my life. Okay, I think those are here. Uh, yeah. Mm, okay. I think you can check my slides. Uh, you are probably able to see my slides, right? So let's see. I'm gonna just check that on YouTube. You are able to see. Uh, I need to also as well check the. Yeah, you are able to see it right now. Okay. Okay. Well, so in meantime, it's gonna be. Yeah, I'm gonna try as well to follow your questions. Let's see. Just for a minute, please. Just give me a second, please. I can try to find if you post some questions. I don't see any question, but I'm gonna at the end of this 25 minutes, I'm going to check the questions. Okay. Okay. Let's see. Let me go over just over here. We were mentioned this previously, right? At the beginning of this session today, we were mentioned about the International Quantum Discovery Day. So, yeah. And we said that this is inside the International Quantum Initiative, in particular in Latin America, we are going to push this initiative with Caldas and QMexico, and with more people and also some different uh, potential partners that in the future we are going to join us. Okay. And this is because, as we were talking with particularly with Dr. Julio Gonzalez, he mentioned that we in Latin America, we don't have, or we need to boost this kind of technologies. Well, quantum computing, as well, emerging technologies. Yeah, similarly as artificial intelligence. Okay. Um, this is why we are doing this kind of activities. And actually, it's if you check, this is very, very important. And as well as Dr. Gonzalez mentioned about the in terms of money, how the amount of money that this kind of topics just move about the different kind of companies, right? And also how the countries can get or improve their economy in when they invest money in this kind of technologies, right? So we mentioned about the what was that? IBM. IBM actually has right now part of the hardware developed so far. This is only some examples that I took from the IBM website. You see here Eagle on your left-hand side. Also at the center, you see Heron, and on your the right-hand side, you see Nighthawk. Okay, so you see, for example, on this left-hand side, the number of qubits. For Eagle, it has, let's see, admit some people. It has 127 qubits. You remember that we were mentioning about the qubits, physical qubits. Let's see. Sorry, somebody wants to Janice, let's see. No, yeah. Okay. Um, so we were talking about the number of qubits, and we said that we need to improve this kind of technologies to increase the number of qubits as well, right? And also, we are going to see here about Google. Google as well produce some chips or just this kind of hardware. And also they don't have here the number of qubits actually, but they have the actually one chip or one device, quantum device, is focused on quantum error correction, and the other one, it's about the random circuit sampling, right? Which was one topic that we were talking about, the quantum error correction, which is one challenging topic when we want to improve the quantum technologies, right? This is one challenging part. Okay, let's see. Okay, so this is about my talk. I want to mention why we are talking today about this kind of things, okay? And this is because all these different topics are coming from the quantum mechanics. And quantum mechanics is one field that was that started at the last century, right? Actually, the one of the problems somebody said about the problems in 19th century that there is nothing new to be discovered in physics now. All that remains is more and more precise measurement. It was attributed to Lord Kelvin or William Thomson, which was the same guy, but probably this quote was attributed as well Albert Michelson. It was about around 19, okay, 19 the last century. Well, but today in our current century, I mean the perspective in 21st century. Oh yeah, I have a typo over here. Science is ongoing journey. Okay, so we know that the science is moving forward every day. Actually, one of the things that we are working currently is because science is not an area that it is only static. Science is continuously dynamic. Okay, it has a lot of dynamic inside. There are people working in science around the world. But unfortunately, we don't know all about the different things that people are working because science uh, improve and boost and move forward, but all the different knowledge doesn't have immediately an application immediately. It takes time because that is, science is coming from our knowledge, but that knowledge is abstract knowledge. So when science starts to grow, usually it's an abstract idea. So in the future, this idea start to move forward, and then it's going to probably produce some applications. Okay, so quantum mechanics was coming from those abstract ideas. Actually, the quantum mechanics was remember this previous quotation. Yeah, somebody said we don't have anything else, any kind of new things are coming from the current science. It was in 19th century, but one idea was what happens with the body radiation. We don't know actually how we are going to describe that kind of phenomena. So actually, Planck proposed a solution, and there were different kind of solution actually. But Planck, he proposed a particular equation. It's over here on bottom on this slide. And with that equation, we can describe the radiation, the body radiation. And you see on this figure with the different colors, which is the spectrum, you see the visible spectrum. That is that we can see, that we as a human can see, right? So actually, if you check over here, this is 1, 2, 3, 4. This is 4 micrometers and 5, 6, 7, around 7 micrometers. That's the wavelength. Okay, so that is the visible wavelength for us as a humans. We can see only in that window. That is that we can see with our eyes. Okay, but the energy, or a body is radiating energy, as you see in this particular plot from here we are just showing the micrometers wavelength, but we will have different scales, okay? So this is just one example. And actually, as well, we can see that we have different temperatures, right? So you see, for example, here, a body radiating energy of at 3000 Kelvin will have this curve over here. And at that energy, we only will be able to see this small part on this region, right? Okay. So well, we will have a similar for 4000 kelvins, 5000 kelvins, and 6000 kelvins. So that is going to be the different curves for one body radiating energy at different temperatures. Okay. Actually, this plot, as you see here, it's well, let me see, the sun in the center of a galaxy. Yeah, this body is radiating energy at around 7,000 Kelvin. So this is how our sun radiates energy. Or a star similar to our sun radiates energy. This is how we can describe the how one body radiates energy. Well, another important thing about this, it's if you check this equation here, we see the Planck's constant, which is one slide that I show you. Let me go over there just to answer why are we celebrating currently this today, the World Quantum Day, because that constant, Planck constant, is 4.14. And Planck, yeah, found that he needed this constant to construct this equation, actually. Okay, so you see over here, you also see over here, and you did this function. Oh, sorry, just give me a second. Sorry. So you see here that this function is in terms of the the frequency, and t, temperature, and that's why you see the different cubes over here, right? The rest of the things are just constants, numbers, such as the Planck constant, pi, and c, which is the light, okay, speed light. Well, okay, so let's see. So the quantum mechanics comes from those abstract ideas, and we after can analyze different kind of phenomena thanks to these ideas that actually Planck and other people such as Heisenberg and people that we previously mentioned developed to analyze and to understand the nature. So in this slide, I just want quickly show all of you some phenomena that we describe with the quantum mechanics using all this analysis and the theory that was developed kind of one century ago. Okay, so you see, for example, the photo disintegration, current scattering, Compton effect, photoelectric effect, and well, some more other different phenomena. Okay, but what about quantum information? Quantum information is very interesting topics. Well, quantum ideas, okay? Well, or quantum concepts, okay? So quantum information took or takes some ideas coming from quantum mechanics and implemented in computing, and then we have this quantum information concept. But it is not the only one. It has three important fields or branches. So the first one is quantum computing, second one quantum information theory, and quantum cryptography. Okay, so let me just show you quickly more about the quantum computing. The quantum computing is over here. Actually, I also mentioned Feynman some slides ago where we were talking about the foundations and also people who developed part of the quantum computing. Actually, Feynman was the scientist or physicist who proposed this quantum computing area. And he wanted, or he was thinking about the simulation where with the quantum systems on classical computers. At any time, those to become impractical as a system size increases. Actually, that was part of the thing that we were talking with Dr. Hannah and as well Dr. Julio Gonzalez, right? But well, he proposed that about 1980, 81, okay? So it has around 40 years ago, the quantum computing. And then David Deutsch, he started to formalize this thing. This is the paper. You can find this paper. I don't know, maybe different repository you can find this paper. But he's David Deutsch, and he proposed or formalized more this field, which is that we know as a quantum computing. Okay, things that quantum computing are using are something like entanglement, things that are concepts that actually we also were talking about with Dr. Gonzalez and Dr. Henne. And this is the idea where we have those two particles, we have those two connection, those two are entangled, those two particles have or are sharing some properties, some things. Okay, so that's part of the entanglement concept. And the other one is the superposition. And superposition, as you know, it's this idea where we have one thing cat or particle into potentials, and into potential or into states. Okay. Well, so actually, this is how we can see the qubit over here. So this state is in terms of this qubit 0 and qubit 1 and alpha 1 and alpha 0, where those two are things that we know as amplitudes. And this notation is called bracket, or sometimes people call as well as a Dirac notation. That's as well coming from physics. And this is the difference between, different to the, oh, let's see, somebody's joining, or let's see, just let me check that. Oh no, I think everything's okay so far. So, the quantum information has, see, yeah, somebody was coming. Yes, is our next speaker. Well, so yeah, I was mentioning that here with this part, we represent the state in terms of those two qubits, and that's that we call as a superposition, which is different to those two classical perspective where we have only zeros and ones, right? 0 and 1, those two different states. And but yeah, when we introduce this previous concept that we were talking about, then we have this superposition. Okay, well, let's see. So, so with quantum information, we want to source and store and transmit information, and actually we need those to be encoded, actually, or we need to be save this information, and that's the other branch that I mentioned previously, which is the quantum cryptography, and cryptography actually has those three different branches as well, but we can define cryptography as the discipline that embodies the principle, means, and methods for transforming data to hide their semantic content, prevent unauthorized use, or prevent undetected modification. This is just one. I know that probably you will see a similar or different, or yeah, the same idea with different words for the definition, for the cryptography definition. Okay, so no worries about that. The only point with the cryptography is actually part of cryptology. Cryptology is a field, a huge field that contains cryptography, and cryptography has those three different branches. Okay, but with cryptography, we want to send information. We need to transmit information from one point, A point, to one B point. This is the simple one. On top, you see this diagram over here. And with that diagram, I only want to show that we want to transmit information, but to do that, we need to encrypt information over here. And to do that, we need a key. That's the key. And then the message travel in a medium, in a mean, which is the classical channel usually, right? But the quantum information or quantum cryptography, we need a quantum channel. So over here, we need the message again to take the message and then use the same key, because this guy at B point needs to decrypt information, right? So that is basically, or actually, the idea with cryptography. We have a message, we send a message, we encrypt the message, we send a message, we decrypt the message, and then we can check the message, the original message. So, and that's the same idea in quantum cryptography. So this is I'm going to show you the RSA asymmetric algorithm. It also uses a public key, and that's one algorithm that we currently use in some of different websites or different parts of technology to encrypt information. So suppose that we have this diagram with 5 guys over here, and each of these we have a message, and also they will have a key as well. Okay, so they are going to connect all of this. Maybe I don't know if you can see, but if you see, all of these are connected in pairs. Okay, they are pair connected. This with this one is 1, 2, 3, 4, and 5. And so 1 is connected with 2, so on until 5, and 2 with 1, 4, and 3, and 2, and so on, right? Each of these are connected. So something that's over here in the middle, at the center of this slide, you see button that we have this diagram where now we have this public key, right? This is those guys are connected, and now we have this public key. And then, for example, suppose now on the third diagram over here, this number 1 guy wants to send a message, which is over here. So this guy is gonna use the public key and then encrypt the information. So when the message travels, and then use the decryption algorithm, which is going to be the inverse function usually, and get the original message for the guy number 3 over here, right? So that is basically that we use in simple words that we use in quantum cryptography, and actually cryptography. But quantum cryptography, we are going to use the previous concepts that we mentioned, such as entanglement, superposition, and other concepts coming from actually quantum mechanics, right? Well, so we have 5 minutes, perfect to finish this part. But I just want to show you, as Dr. Julio Gonzalez mentioned, some of different tools that different companies provide to do simulations with quantum computers. Even sometimes you can also use real quantum computer depending on how many qubits you want to use. Okay, so some of different companies are such as Amazon, Rigetti, D-Wave, Intel, we have Xanadu, Google, IBM. All of these usually are going to use Python. Sometimes they also have Jupyter environments. Oh, I forgot this, Mathematica, Wolfram Mathematica. They also have some packages to use do quantum computing. And well, Collabs, which is similar to Jupyter's, and also you can use Python as well. Okay, so this is some of the different companies. Uh, Unfortunately, currently we don't have any Latin American company doing providing services with quantum computers. But well, in the future we hopefully we are expecting that. Okay, so well, if you are curious about the how to get the knowledge about this. As well, Dr. Julio Gonzalez mentioned about some courses, or probably they also mentioned some different websites and also tools where you can find more information about this. But my recommendation as well is if you want to check quantum computing, quantum machine learning, those are books that you will need. Okay, so it is better if you check those books just as how we can say part of your background with our current quantum technologies and machine learning technologies, which are everywhere in our world. So this is famous book, this one, Artificial Intelligence, Modern Approach. This is another one about machine learning. This is more about machine learning, math for machine learning. Quantum computing is interesting books for computer scientists. This is more about cryptography. This is algorithms, handbook math. This is interesting to check some math concepts that sometimes we also missed or can miss. So this is about quantum computing, quantum mechanics, sorry. This is famous book actually, quantum computing and quantum information. This is the Nielsen and Schramm book. And this is Michael Sipser. This is about algorithms and basic about um, computational theory. This is about the statistics because in machine learning we use a lot of statistics. This is as well more about computational theory, more about this. Oh, I have twice this one, but maybe it's because it's very important as well. So this is an interesting about quantum machine learning. This unfortunately was well, we missed this guy, Peter Wittek. He wrote some interesting papers in this book as well. You can find more details about his life in different social media and also different websites. This is about the math and particularly math and for physical sciences and quantum mechanics and well, linear algebra, very important topic in quantum machine learning and also quantum computing. Okay, well, math, physics, and Lee if you want to work with more theory. Okay, so those are part of my recommendations. So thank you guys for this. This is perfect time to stop sharing and check potential questions. Let's see, because our next speaker is it's over here. So I'm just going to check if we have some people. Let's see. Try to find yeah, over here. Maybe potential question. Let's see. Remember, guys, you can pose your question in Spanish and English. So no worries. We will try to cover all of them. Let's see. Do you think we should have? Let's see. Yeah. Do you think we should have prepared for AI as we should prepare for the quantum era in terms of cybersecurity? Yeah, the answer is yes, we should. We as a scientist should be worried about this, should be aware about this. And this may be independently of your background, probably biology, biochemistry, chemistry, physicists, whatever you are enrolled currently. But yes, it is really, really important to be focused on this and prepared about this kind of technologies. Uh, okay, there is one more in Spanish, but I'm gonna try to cover this after or talk from Powell, okay? So let me stop over here and then just introduce Powell Gora, okay? Because Powell, he also has a different time zone, so it's better to start with him, okay? Okay, Powell, welcome to this session and thank you so much for joining us.
Thank you. Thanks for the invitation. Okay, so I can tell you that I'm joining from Poland, so it's already 30 minutes after midnight. But I hope I will manage to give a talk about keyword to you.
Yeah,
So let me share my screen. So happy World Quantum Day to the quantum community in Mexico, first of all.
thank you.
So actually, it's already April 15th in Poland. We had our quantum meetup yesterday in the evening, but I managed to return home to give this talk for you. All right, so my name is Paul, and I'm currently the chairperson of the board of QWord, and I will tell you about QWord today because this is a good place for quantum education and also some research internships in quantum technologies, so I will tell more about it. I'm also a coordinator of the Q Cousins department of QWord, and I will also tell more about the Q Cousins department because actually Javier is also the leader, the coordinator of one of our Q Cousins, QMexico, while I'm the coordinator of Q Poland, so we are quantum cousins in some sense. All right. So, what is QWord? So, QWord is a global network of individuals, groups, and communities collaborating on education and implementation of quantum technologies and research activities. Um, it was established in 2019, so already more than 6 years ago. We have several departments. We've organized more than 200 events, perhaps close to 300 already, and we've handed out more than 10,000 certificates. I can estimate that it's probably already more than 15,000. And yeah, um, this is the current structure. So, as I said, I'm the chairperson of the board. We have a few other board members. So, we are now in the something like a intermediate pro. So, we are in the process of transforming keyword, reorganizing keyword structures as well. So probably soon, maybe later this year, the structure will be outdated. So I've already decided to step down from leading keyword after serving as the chairperson for more than 2 years already. So there will be probably a new board soon, but as for now, I'm still coordinating this organization. You can find more information about it in the Keywords website. It is also important to know that it's formally and legally um, supported by a non-profit organization that is called Keyword Association. So it's an association, it's a non-profit organization that is registered in Estonia, in Europe. So here we can also see the structure. And we have three merit departments: Q Education, in which we work together internationally to develop open access educational materials. And we also train educators to bring quality education in quantum technologies. Um, and there are also two other departments: Q Cousins department. So our Q Cousins are local groups in different countries all over the world. And as I said, we work together globally to develop educational materials. And then we use these materials to organize workshops for our communities in our countries. Um, And we also have a Q research department. As you can imagine, this is a department responsible for research, and it organizes a program for research internships in quantum technologies. Okay. All right, let's go further. So currently, QWORD is one of the largest quantum communities worldwide. So I can tell you that there are more than 3,000 people. Oh, sorry, there are more than 3,000 people on Discord, and actually, this number of Q cousins is also slightly outdated because currently we have 41 Q cousins entangled with QWORD, but some of them are currently inactive, so it's roughly 50-55 Q cousins. As I said, we've organized more than 200 workshops and handed out more than 10,000 certificates. We offer several quantum computing courses, starting from the preparation, like giving the background in linear algebra and Python programming. It's called QPrep. There's also an introductory level workshop. It's our flagship workshop where the participants can learn the basics of quantum computing. It's called QBronze. And then when you are already quite advanced, then there are some intermediate level workshops, QSilver, focusing on Shor's algorithm and quantum Fourier transform, and QNickel, focusing on oracular quantum algorithms, so quantum algorithms with oracles. There are also some self-study modules focusing on quantum annealing, quantum error correction, topological quantum computing. Yes, so these are just different educational materials that we offer. Beside the workshops, because our workshops usually last about 15 to 20 hours, so they are usually we usually divide the materials in 4 or 5 sessions. But sometimes we also organize longer open online courses like QClass. So QClass is our program for the whole complete quantum semester. We also organize an internship program that's called QIntern. It's some kind of a matchmaking event for online research internships in quantum computing. Every year we receive about 500 applications, so usually between 4 and 600. And people from all over the world can first propose ideas for their research projects, and then candidates for interns from all over the world can apply, and we match them, and then the interns can be guided by the mentors, senior mentors. They work together during the summer, and at the end of the summer, they present the results of their work during something that we call a demo day. There are also some other quantum programs that we organize, webinars, where we invite some notable speakers, and Q challenge. So we challenge our Q cousins to be active and to organize events for their local communities. So now a bit more about the Q education department. So as I said, this is a department in which we work together to develop educational materials. What is very important, all these materials are open source, available under Apache 2 license. They are available for free, so everyone can use them. You can go to the website and just review the material. So they are in the form of Jupyter notebooks written in Python in Qiskit framework. We are now also trying to translate some materials to Pendelane. And we work, as I said, we work together internationally, just not to duplicate the work in different countries, but then we offer the courses, workshops for our local communities in our countries. QPrep is a, as I said, preparatory level workshop, so you can see the scope. So there is an introduction to Python programming, there is a basic math basic linear algebra, and actually there's no prerequisite for joining this Q prep, and you can check the repository. And if you already have some programming skills in Python, and if you know the basics of linear algebra, then you can take this introductory level course that is called QBronze. And here you can learn the basics of quantum systems, like you can learn about quantum circuits, quantum registers, quantum gates, measurements, execution of your circuits, reading the outcomes, yes, quantum operators on the quantum bit, entanglement, and also with quantum search algorithm, the Grover search algorithm. Uh, in QSilver workshop, you can learn more about the block sphere, the quantum Fourier transform, and Shor's algorithm. And the end, the Shor's algorithm for factorizing large numbers. QNiCal is another intermediate level workshop. So here you can learn about some quantum algorithms with oracles like Deutsch's algorithm, Deutsch-Jozsa algorithm, Bernstein-Vazirani, Simon's algorithm, and again Grover's algorithm, but this time applied to the MaxCat program. Okay. QCousins department is another department that we have. As I said, these QCousins are local groups in different countries collaborating together and operating locally, serving their local communities. Like here in Poland, we have Q Poland, but in Mexico, you have QMexico that is coordinated by Javier. And yeah, so these Q cousins collaborate. Like I also decided to support Javier and QMexico by giving the talk today. And we just support each other just to enhance our activities. And there is this Q research department. Um, so we used to have some study groups where people met once per week or two to discuss some research articles, but at some point people just were too busy and it was difficult to keep it. But there is this one very successful project in the Q Research department that's called Q Intern. So as I said, this is something like a matchmaking program for online research internships in quantum technologies. So here you can see the timeline for this Q Intern program in last year in 2025, and very soon we'll also open the submissions for project proposals for this year's edition for 2026. And later in May, we'll announce the list of projects. So usually we select something like between 15 and 20 projects for the internships. And then there will be a call for interns. And everyone can be an intern. So you even do not have to be a student to take this internship. So you can be a high school student, you can be a graduate, you can be a researcher if you would like to take the internship. But usually, most of our interns are students. Yes, so there is something like a recruitment phase where we just match the mentors with students, and later after they are matched, they work together during the summer for several weeks. And at the end, there is something like a mini workshop or demo day where people present the outcomes of their projects. So here you can just see some examples of the projects that we had in 2025 and the names of the mentors as well. So now, just at the end, a few words about Keyword's mission and goal. So, in general, our mission is to provide an opportunity for free education in quantum technologies for people all over the world, to popularize quantum technologies and their use, to enable research opportunities and contribute to training the next generation of scientists, to maintain a community of enthusiasts of quantum technologies and provide a platform for their communication and collaboration, We would like to integrate QWord with the global open quantum ecosystem that's also growing together with QWord. We will also like to organize educational events like workshops, hackathons, lectures, and to maintain our local groups, Q Cousins, in many countries. We would like to have at least 50 active and sustainable groups by the end of 2027. We'll see. So this is our goal. We also like to have the active community of enthusiasts of quantum technologies sharing and their knowledge and contributing to discussions. And regarding our Q cousins, we would like to give them the opportunity to meet virtually or in person at least once per year. So that's why last year we started organizing something that we called Qword Annual Meeting. It's held in January every year. We are also planning to organize this Q intern program at least by the end of 2027, but it's one of the most successful programs in Qword, so I believe that it will be continued even later. And we are also planning to continue developing educational materials and achieving long-term financial and operational sustainability is one of the challenges for us, but we would like to achieve it soon. And we would like to be an active member of the global quantum community and participate in keywords related, quantum related worldwide events like World Quantum Day, like we have it today. We have several partners. We collaborate with companies like Eureka Classic, with organizations, non-profit organizations that Unitary Fund, Womanium, Open Quantum Institute, with several universities like New York University of Abu Dhabi. We organize workshops for the participants of their hackathon in Abu Dhabi every year. So this year it will be in August or in July and August, as far as I remember. If you are interested and would like to learn more, let's stay in touch. So here you can see some links to our social media profiles, link to our Discord server, where you can join to participate in discussions. As I said, we have more than 3,000 people there from all over the world. You can subscribe to our YouTube channel, where we also publish some recordings from time to time. With this, I thank you for the attention, and if there are any questions, I'll be happy to answer. And here you can also see an email address to QWord. So you are also welcome to contact us, of course.
Paul, we appreciate your time because, yeah, and thank you so much. We know that you have a different time right now. So, yeah, I'm gonna check if somebody has some question. Just let's see. Uh, but in meantime, I have a question, Paul.
Yes,
So let us know and tell us more about the in Latvia. Are you right now in
in
Poland or in
Poland.
Latvia? Oh,
I'm in
sorry.
Poland. I'm in Poland.
In Poland. How is in Poland the academic environment in terms of quantum? I mean, the universities are started to create programs, I mean, graduate programs, PhDs,
Yes.
masters. Tell us more about that, please.
Yes, yes. So as far as I know, we do not have dedicated PhD programs yet, but we do have some dedicated master programs. So probably the oldest program is an international master studies program at the University of Gdańsk. So it's the north part of Poland. Just earlier, as far as I remember, this in October 2025, so last year, Wrocław University of Technology opened their engineering studies. They also acquired a quantum computer from IQM. IQM is a startup from Finland.
Yeah.
So they acquired a quantum computer from IBM and they opened quantum studies, and I can see that the students, the first year students, already started playing with it just before, just earlier today. There's a student association there, and one of the students sent me an email and told me that they already started doing some experiments on this quantum computer with only 5 qubits, and they are looking for some mentors and some research opportunities and so on. There is a plan to launch another master There's another program in Poznań, at the University of Poznań, and in Poznań there will be soon another. I think that it will be another engineering so undergraduate program at the Poznan University of Technology. So we already, as far as I know, we already have three programs, um, two at the master level, one at the bachelor or engineering level. There will be second engineering level studies program starting from October. And a few other universities also already offer some courses, not the complete studies, but some courses on quantum computing as well.
Okay, well, thank you so much. So, yeah, my question is just to know how is the environment in Europe about this. I know that in Italy as well, they started some programs about quantum computing. So, which is, I mean, it's very interesting and very good. So maybe in Latin America, if there are people right now studying their bachelor degree and they are looking for something about quantum computing, Poland would be a really interesting country to go and maybe submit your applications for
Yeah.
some programs. Yeah.
Yeah, so I can tell you that currently in Poland we are working on the Polish national quantum strategy for the next 10 years until 2036. And indeed, we would like to open more quantum studies and have more international collaborations as well to really bring talented people here and to open some research centers. So there is a plan to
Mm.
allocate significant amount of money until
Yeah.
2036. So it hasn't been formally approved yet, but it's work in progress. But I hope that this program will be approved by the end of this year, because
Oh.
there is a plan to start implementing this program starting from 2027 and until 2036, as I said. So yeah, it seems that there can be more and more opportunities in Poland indeed, but I can also tell you that several other countries in Europe have already prepared and approved their national quantum strategies. So several countries like the UK, United Kingdom, France, Netherlands, they're more advanced, to be honest.
Mm.
Finland is quite advanced as well.
Yeah.
There are some good universities and startups as well. Uh, Italy probably as well, as you said. So in general, this western part of Europe is
Mm.
still more advanced and more just wealthier, right? So they have more money, and their ecosystem for new technologies, for deep tech, is more mature, let's say, more
Yeah.
advanced. There's more funding from the public sector and also
Mm.
from investors. So there are probably more opportunities in the west part of Europe, but this central Europe, on the other hand, is growing very fast. So currently, Poland has one of the highest, rate of growth of our gross domestic product.
Mhm.
So our economy is growing. Poland has recently, just a few months ago, joined G20, so it became the 20th largest economy worldwide, and it's still growing. So the economic
Yeah.
growth is about 3.5 to 4% per year. So it's growing quite
Okay.
fast, one of the fastest growth in Europe. So I would say that Poland is currently as a startup because
Okay.
it's growing quite fast.
Uh-huh.
It has a good potential. So there are some
Sure.
other larger, more advanced countries to the west, in the
Mhm.
western part of Europe. But if you are looking for a place that is growing quite fast, then Poland is one of these places, definitely.
Yeah, thank you, Powell. Powell, we have a question from Gabriel Hanna, and I think this is gonna be the last one because we
Yes,
know, and I'm so sorry for
that's
the
fine.
time.
No worries.
So, okay, the question is QWAR purely volunteer driven, or is there some public-private funding for developing resources and supporting partnerships?
Okay. So it is mainly volunteer driven. So I would say that 95% of the work is based on volunteering, but from time to time, thanks to these collaborations, sometimes we get some funding, but usually this funding is spent for some operational activities like preparing graphics, paying licenses for Zoom, for the server of the website, and so on. Definitely the budget is not big enough to fund even 10% of the work that we do in Keyword, unfortunately. So we can only cover some really important expenses and urgent expenses. And this is one of the reasons why we are still looking for the founder for funding. And this is also one of the reasons why we said that one of our goals is to achieve this long-term financial and operation sustainability. But from the perspective of interns, because you also asked about funding for developing resources and supporting internships. In case of developing resources, um, as I said, usually it's volunteering based, but from time to time we get some funding and we can cover some costs. Regarding internships, as we are rather so this QIntern program is rather a platform, a matchmaking platform, I would say. So we match the mentors with the interns, so everything depends on the mentor. So we leave the decision to the mentor. So if the mentor has the opportunity to pay something, then we allow it, but by default it's also unpaid internship. As we are a global organization, that we already see that in general, transferring money internationally is complex.
Yeah, yeah,
So we already had a situation when we wanted to pay something to people from Nigeria, and it turned out to be technically very difficult actually to transfer money from I do not remember where it was. Was it Poland or Latvia or Estonia? We wanted to pay someone in Nigeria, and it turned out that the bank systems were incompatible, and we're not able to send or transfer money easily. So in general, it's more complicated, right? Most of the work is on volunteering basis, but sometimes if there are some really important crucial tasks for we need to pay, then we also have some rather small budget for this.
great. Thank you so much, Powell. And yeah, Gabriel said thank you.
Thank you.
So yeah, we are going to keep in touch, Powell. Yeah, we are, as you said, we are kind of cousins. So,
Cousins. Yes. Almost,
so
almost a family. Even though
yeah,
even though we haven't met
in
in person
person.
yet.
Yeah, you're right.
Maybe one day in the US, maybe, or somewhere in Europe. We'll
Absolutely,
see.
absolutely.
Good.
Okay, Powell. So
Good
thank
luck.
you.
Have a happy rest of the World Quantum Day in Mexico. And I'm
Yeah,
going to sleep. Bye
yeah.
bye.
Thank you. Have a good night. Bye bye.
Bye
Thank
bye.
you.
Cheers.
Okay, so yeah, so it was really interesting conversation with Powell as well. So I'm going just to this last part. It's going to take about 15 minutes to close this interesting session. So again, thank you for all of you, to all of you guys to be here. Thank you, people on Zoom and also on YouTube. We are going to close soon this session. So I just want to say see you, and please pay attention in our social media. We are going to post more events soon about quantum computing, quantum technologies, quantum machine learning. And just keep in touch. So, now en Spanish, gracias a todos, de verdad agradecemos muchísimo su apoyo, su atención. En redes sociales vamos a estar publicando diferentes eventos acerca de computación cuántica, acerca de inteligencia artificial con algoritmos cuánticos y con conceptos cuánticos. A veces esa traducción del inglés al español no es tan literal y no sé, a veces me pongo inseguro a la hora de traducirlo al español, pero espero que se entienda. Hemos estado hablando sobre computación cuántica desde el punto de vista científico. Ya ustedes vieron que hay diferentes investigadores alrededor del mundo trabajando en estos temas. Hay temas como baterías cuánticas, que es un tema que la verdad solamente conocí, bueno, estuve en un evento y conocí a algunos investigadores, pero de los que conozco en América está el doctor Gabriel Hanna, y es uno de los investigadores y ponentes que tuvimos hoy. Thank you, Gabriel. You are really awesome. We appreciate your time. So, gracias de nuevo y que estén muy bien. Buena tarde y el resto de las personas que están en YouTube, muchas gracias. Ya vamos a cerrar. Espero que estén muy bien y que tengan una feliz tarde. Por favor, síganos en redes sociales aquí en México. Aquí en YouTube también vamos a estar posteando actividades acerca de computación cuántica. Y bueno, pues que tengan una feliz tarde a todos y una feliz noche en donde estén. Y gracias por estar aquí con nosotros. Ah, Parece que alguien va a comentar algo.
No, solamente me quería despedir. Muchas gracias.
Gracias, maestra Alma López. Tengo el gusto de conocerla también. Buenas tardes y hasta
Hasta
luego.
luego.
Hey, Gabriel, thank you so much. We appreciate your time.
Thank you so much, Javier,
You
for
are really,
organizing this event.
no, thank you, thank you. We enjoy your talk. Thank you so much.
Yeah. Have a good evening.
Yeah, you as well. Bye bye.
Bye.